Okay, so I'll introduce you. Today, Renaud is going to be talking about quantum multiple value decision diagrams in graphical calculus.
Let me unmute. Okay, so thanks for the introduction, Cole. And hello to everyone. As per usual, don't hesitate to interrupt if you have any question during the talk. So I'm going to talk about today two different formalisms for representing quantum processes. One, which I think you all know about, which is graphical calculus, like ZH. And another one, which is probably a bit less known by this community, which is quantum multiple valued decision diagrams. So I'll introduce in a few moments what these two are. So as I said, maybe I don't really need to go into the details, but we have two formalisms at hand. The one on the left here is ZH calculus, where we represent quantum processes using string diagrams, where we can visualize quantum information flowing into wires and operations acting upon them using nodes in the diagram. Can you see my cursor, by the way, when I show stuff around? Yeah, okay, thanks. And so the other formalism is quantum decision diagrams, which are, let's say, a weighted variant of decision diagrams that are used usually for decision problems, classical decision problems, and which I'll introduce a bit more in details in a few minutes. So what are the motivations for looking into the connections, let's say, between ZH calculus and quantum multiple value decision diagrams? So first, decision diagrams, quantum multiple value decision diagrams, are an exact representation of a quantum process. And they exploit redundancy inside their representation in order to get more compact. It's already been used for verification, approximation, circuit synthesis, and so on. So there are already a wealth of tools that we could exploit from this connection between the two formalisms. And also another motivation we can have is if you suppose you have a description of a quantum process on n qubits, which is polynomial in the size, in the number of qubits. So actually, imagine you have a description that's polynomial in the suppose you have a description of a family of processes on n qubits, which grows in size polynomial in the number of qubits. So for instance, you could have a circuit description or the description of a measurement-based quantum computing scheme, something like that. So usually we have a good translation between these types of description to ZH diagrams, for instance, but we can also compute the underlying matrix, or we can even turn the ZH diagram into a normal form. So there are already several existing normal forms for ZH diagrams, but we can also compute the quantum multiple valued decision diagram of this formalism, of this process. Sorry. And something that's already a bit important for me, at least, is the uniqueness of such a representation. So if we look obviously at the matrix representation of the ZH normal form, then this one is unique. But it's also true for the QMDD part. The decision diagram of the quantum process is unique. But on the other hand, the ZH diagram that we would get directly by translating from the description wouldn't be unique. We can easily create other ZH diagrams that are completely equivalent. For instance, one of them is the normal form, the ZH normal form. But if we look, on the other hand, at the complexity, the size of this representation, of these representations, we see that, well, the ZH diagram representation, at least the one we get from a direct translation from the description, is pretty nice because usually it's polynomial in size as well. So here I'm assuming we have an efficient translation from this description to a ZH diagram, but it's the case for quantum circuits, for MBQC schemes, and for other kinds of description like lattice surgery. So it's fair to assume, I guess, that this size is polynomial. But the matrix and the ZH normal form, the size of these two representations obviously are exponential. Whereas the size of a QMDD can range between being constant and exponential, actually. Why? Because it exploits redundancy in the representation. So that's why it's interesting to look at this formalism and the links between the ZH calculus to see if we can draw some interesting insight from the decision diagram part. Okay, so now I'll introduce the ZH calculus. I'll go quickly on this because I think everyone here knows in general what it looks like. So the ZH calculus is formed first of diagrams, ZH diagrams, that are string diagrams generated essentially by these two generators here. So the first one is a white node that we call the Z spider, which has arbitrarily many inputs and outputs. So I read my diagrams from top to bottom. So this one has n inputs and m outputs. And then we have an H box called H spider, again, which has arbitrarily many inputs and outputs, and which is parameterized by a complex number, R. By default, this number is taken to be -1. So if you see an H box with nothing in it, then by default, it's taken to be -1. These generators are then composed in two different ways to form larger string diagrams. For instance, this allows us to define two new spiders, which we'll call X spider, by composition of the white node and the H spider. So if you're more familiar with the ZX calculus, these two new spiders are essentially the red node and the red node parameterized by pi of the ZX calculus. Okay, then we understand these diagrams as quantum operators using the standard interpretation, which maps any diagram of ZH to the category qubit. And I want just to emphasize on two interpretations, which are the interpretations of Ket0 and Ket1. So the two states of the standard basis, which will be important in the following. That's why I'm emphasizing them right now. So yeah, here I have an example of how to compose set generators, but I think here everyone knows how to do that, so I'll just skip this part. And now maybe something you're more interested in now. What are quantum multiple value decision diagrams? So as I said, those diagrams are an exact representation of a quantum process. But for the sake of simplicity, in the following, I'm going to use the map state duality and consider that all the operators or all the quantum operators I'm going to consider are given in the form of a quantum state, actually, using this map state duality. So, for instance, I could give you the full formal description of a decision diagram, but it gets a bit convoluted quickly. So I'll just go through an example, and I think you're going to understand pretty well how it works. So let's say we have a qubit quantum state. So it's a qubit state because it has size a power of 2, actually 2 to the 4. So it's a 4 qubit state. And because it has size a power of 2, we can first arbitrarily describe or create a tree upon it, a binary tree, such that all the entries in the quantum state end up being leaves in this tree. So this might seem completely arbitrarily, but actually it's pretty natural because Every layer in this tree essentially represents a qubit. And we can easily get the amplitude of one of the basis states by simply moving inside this tree. So for instance, if I want to know the amplitude of the state 1100, I simply have to move in this tree by deciding at each node whether I go left or right, depending on the bit in the bit string. Okay, so I think it's pretty natural. And now we're going to turn this tree into a decision diagram, and we're going to exploit redundancy in order to compact everything, to make everything more compact. So the first thing we do is we're going to move the weights, these, well, the complex number inside the leaves onto the edges. So we are going to artificially create a terminal node here that I represent with a box, which has nothing to do with the edge spider, but it's represented as a box as well. And now the edges become, well, the weights, sorry, become weights on edges. And then we're going to exploit redundancy, as I said. So the idea is basically that if you're at a node and going left or going right is essentially the same, then we can just regroup the two outgoing edges. So for instance, here we have a node whose left and right edges have weight 1 over square root 2, and which are both linked to this terminal node, so we can simply fuse them together. Oh, sorry, I did this for these two edges first, because they have weight 0. Then we can do it for weight 1 over square root 2 here. There are several other places where we can do that, so just move ahead. And then we create a new opportunity for using redundancy here. So again, we can merge the two edges. Now we have a slightly different situation where you have this node. You can see that you have the two same subdiagrams for the left and right child. So we can again merge them together and get this diagram. Now we might think we're done, but actually we're not, because there's something in common between this subdiagram, and this one, which is that they are not equal but collinear. So now we'll have to move weights around in the decision diagram in order to be able to see this redundancy I'm using in order to make everything more compact. So I'm going to move this minus I here at the top of the diagram, well, one layer above, actually. So here, this creates a new subdiagram, which is 1, 0, which is the same as this one. But before I merge them, I'll do the same here. Again, remove this weight up. And now we have 3 instances of this same subdiagram that we can merge together. I think we're not done yet. We can still move this weight up, and this creates again 2 instances of the same subdiagram, so we can merge them. Might not be completely clear, but these 2 nodes here have the same 2 subdiagrams, so we can merge them. And just for completeness, I'm going to finally move this weight up. And so that's the reduced QMDD, the reduced quantum multiple value decision diagram we get from this quantum state I started with. Okay. And notice that we can still recover fairly easily the amplitudes at given basis states. So the same example as before, if I want to see the amplitude for the basis state 1100, I still simply need to move around in this decision diagram. We go 1 to the right, 1 to the right. Here, I'm jumping over 1 layer, which means that the 3rd bit in the bit string doesn't matter. And so when I arrive here, I have to read the very last bit, 0, which says that I have to go to the left. And we recover this weight minus I by simply multiplying all the weights we went through on this path. Okay, so it's clear for now? If not, don't hesitate to interrupt. Okay, so we have here a representation of a quantum process that, when expressed like this, actually, well, at least is pretty graphical. And so something that's very natural to me, at least, is to ask the question whether we can map such a QMDD, such a decision diagram, directly to a ZX or a ZH diagram in a way that's efficient in some sense. And that's what we're going to do now. So the next section is devoted to a recipe that explains how to turn a QMDD into a ZH diagram. So to do that, I'm going to first use a bit of syntactic sugar. I'm going to introduce two new nodes, which have actually already been introduced in the literature, but I'm going to reintroduce them now. So the first one is this diagram, which we understand as being an operator from 1 qubit to 2 qubits, and which is controlled by a fourth qubit. The reason for this is that we can understand this diagram as being a diagram such that, well, the control wire controls whether or not the identity and the Ket0 here are swapped or not. So if we plug in Ket0 on the control wire, we get the identity on the left and Ket0 on the right. And if we plug in Ket1 on this side, on this control wire, we get Ket0 on the left and the identity on the right this time. Okay, so that's the first gadget we had. The second gadget was already introduced in the paper Completeness of the ZH calculus, I think, which is again which is this time, sorry, a 2-to-1 diagram defined like this. And for those who know about ZW calculus, it's actually nearly a generator of the ZW calculus, because it forms the product of one of the monoids that constitute the basis of the ZW calculus. But anyway, still we are going to use this fact because actually, so this diagram together with Ket0, it forms a commutative monoid. And so in particular, that allows us to define a generalized version of this node that has arbitrarily many inputs, which we are going to use extensively in the following. Also notice that in this generalized form, if we only have one input qubit, then it simply amounts to the identity. And if we have 0, this amounts to Ket0, the unit of the monoid. Okay, so now that we have those gadgets, it's fairly simple to map a QMDD into a ZH diagram. So the translation goes as follows. Every weight on a wire, so, well, first of all, every wire remains a wire, so every edge becomes a wire, if you prefer. Every weight on edges becomes an edge spider with this weight as a parameter, and which is linked to the wire by Z spider. The terminal node will be mapped to this diagram here, and every node will be mapped to the composition of the two previous gadgets. So as you may notice, this introduces a new wire because of the control wire of this gadget. So we may have more wires than needed, and actually we have to regroup all the control wires coming from nodes of the same depth in the diagram into a Z spider, the output of which will be the output qubit of the diagram of the quantum state. Okay, that will be a bit clearer in the following because I have an example just laying around. And the final thing we have to do is we apply cat1 on the root. Okay. So let's see on an example how it translates. We start with, again, the same decision diagram here. And the first thing we do is we plug in cat1 on the root. And then I'll just move layer by layer from top to bottom. This node becomes this gadget, and we take the control wire and turn it into an output. Then we have the second layer where we have two nodes here. So these two will be mapped to these two gadgets, the control wires of which we aggregate using a Z spider. And again, we draw a wire from this Z spider to become the second qubit of the resulting quantum state. Then we have this weight lying around, which we turn into this H box. And then I think you've understood. We just do that for every layer in the diagram. And finally, we just have to turn this terminal node into this diagram. And so now we have a purely ZH diagram that represents exactly the same quantum operator as the one we started with. So this is obviously a theorem, which is that the translation is sound in the sense that the ZH diagram we obtain from this translation represents the same quantum state as the one that was represented by the QMDD. And okay, we can we could prove this formally, but again, I would just want to give you the idea of the proof, of one of the proofs actually. So I'll just do an example again with this always the same diagram, and with again the bit string 1100. So to understand what's going on, we just have to remember that this gadget here is a control swap on the identity and cat0, that these two diagrams constitute a commutative monoid. And also I'm going to add this little equation that essentially tells us that cat0 moves through the edges by simply eating the weight and doing nothing with it. Okay, so let's see on the example what it does. So if I plug in bra 1100, sorry, I should recover again the same weight minus I, because it's the one we get from the previous QMDD, the previous examples. And so we're just going to to derive everything and see that indeed at the end we do get minus I as the amplitude. So first we just move things around and copy this bra1 through the Z spider here. We get this, and now we're going to use the fact that this is a control swap. So if I start from the top here, we see we control this control swap by cat1, which means that we are going to swap here. We are going to route the incoming wire to the right. Okay, and we are going to just plug cat0 to the left to get this. Then we can do the same for second layer. Again, the incoming wires will be routed to the right, and cat0 will be plugged to the left. Then before going on, I'll just do a bit of simplifications. First, we're going to use the fact that this is a commutative monoid. That means that this diagram here is cat0 simply. And then we're going to use this equation to simply remove this branch and merge cat0 with this node by the fact that it's a monoid. Okay, then we go on. This gadget here is controlled by 0, which means that this time the incoming wire is routed to the left, and cat0 will be plugged to the right. Again, we do the two same simplifications. We can remove this part here, and we can remove this branch that was hanging. And finally, one last transformation we do. Again, this is controlled by 0, so this incoming wire is routed to the left, and cat0 will be routed to the right. So we get this. Again, we can use the two same simplifications to get rid of this branch as well as this this gadget here, and we end up with this diagram. So here I could have simply moved cat1 around and recover the weights, the amplitude we want. Actually, I just left this here so that we can see that what we did was really just following the path that we would have followed from the QMDD, from the decision diagram. And it's pretty natural, actually, because that's exactly what this control swap does. Okay, it simply says whenever I have 0 coming through the control wire, I'm going to route everything to the left, which is the same as what we do when we move around in the decision diagram, and we read the bit string 0. And obviously, when we read the bit string 1, we go to the right, which is what we do here when we plug in cat1. And so then we just have to do a little bit of ZH calculus, of ZH derivation, and we do indeed find that it's the weight minus I we get. So that's an idea of the proof. And now, once I've done that, I think one natural question we can have is whether or not we can go the opposite way. So if I have an arbitrary ZH diagram, can I turn it into a form that we would have got from a QMDD, so what I call a QMDD form? And the answer again is yes, we can do that. Obviously, this is not always efficient, whereas the mapping from QMDD to ZH is efficient. It's linear in the size of the starting QMDD. But the size of the QMDD itself can be usually larger than the one we get from a ZH diagram. Anyway, so okay, but so for this part, we're going to use the fact that actually half the job is already done. Why is that? Because there is one normal form that already exists for ZX and ZH diagrams, which essentially gives us the tree form of a QMDD. That is the most expanded QMDD you can find. So if you want a completely unreduced QMDD. So for instance, with the previous example, as always, I would have gotten this diagram. And so you can see that it's really the same form, except we have done the effort of compacting everything, of using redundancy in order to make things more compact. And so the proof for this went as follows. We first show that every generator of the language can be put in normal form. And then we show that compositions of diagrams in normal form can themselves be put in normal form. And this gives us, well, this shows that, well, we actually have completeness for the language. But here we simply have to adapt this proof for our case, which is the fact that, well, we don't have just a binary tree, but we can have any quantum decision diagram, any ZH diagram in quantum decision diagram form. Okay, so that's the theorem. Any ZH diagram can be put in reduced QMDD form. And the fact that this reduced QMDD form is unique gives actually a new completeness proof. But it's not very interesting because it's not very far from the previous completeness proof we had. But really the crux here is the fact that it's reduced. So So here we just have to, in order to adapt the proof from the previous one to this setting, we simply have to show that we are able to reduce the ZH diagram in QMDD form in order to show the completeness. And so we are just in the following going to look at the reductions we can do on QMDD and how they translate in ZH. And we're going to see an interesting structure, let's say, that will arise. So the reductions we can do with a QMDD are the following. First, we have two rules that just tell us how to move weights around in the decision diagram. Then we have a rule that tells us that whenever we have an edge with weight 0, then we can just simply route this edge to the terminal node. The reason for this is that whenever you have a path that goes through this edge, then the resulting amplitude you get will always be 0, no matter what. So we can straight away reroute this one to the end of the path, to the terminal node. But doing so can create node with no parents at all, which we can simply remove. Again, this can be understood using paths. So such a node is simply a node that will never be reached by any path from the root. So we can simply remove it. Then we have this rule that tells us that whenever we are at a node and the left and right children are actually the same and the weights are both 1, then we can just merge the two nodes together. And finally, we have this rule here that says that whenever we have two nodes that have exactly the same neighborhoods, then again we can merge them together. Okay, and this is enough to get from any QMDD to a completely reduced QMDD, which is unique. So let's see first how we get this first rule, or these first two rules, which are the propagation of weights. These two can, with a bit of ZH rewriting, can be obtained from this equation, which again can be reduced, can be split into simple rules, simple equations, which are this one, which simply tell us that this gadget here, an edge box with arbitrary number linked to a wire by a Z spider, can simply be distributed through this gadget as well as through this one. And it's a bit interesting to dive a little bit deeper to see where this comes from. So the first one comes from this rule, which is bi-algebra rule between this monoid and, well, this part of the monoid and the Z spider, which is one of the axioms of the ZW calculus, actually. So it's very natural to see it here. But if we look at the similar, let's say, the similar equation that gives us the bottom part here, it also kind of looks like a bi-algebra rule, but it's not, because, well, simply this gadget doesn't form a monoid. So obviously this can't be a proper bi-algebra, but still it satisfies this equation, which looks a lot like a bi-algebra. Okay, then we have the next rule, which is the elimination of co-leaves. So simply we remove nodes that don't have any parents. And these can simply be deduced from ZH by simply showing that when you plug in K0 at the top of this gadget, you simply destroy the gadget and diffuse this K0 to the weights. And then we use this equation as well to simply remove the weights along the way. Then we have this reduction that again looks pretty nice in ZH because it comes from this equation. Again, it kind of looks like well, something that we know about, which is the property of a Frobenius algebra of being special. Although, again, it's not a Frobenius algebra, obviously, but still it kind of looks like it. And finally, we have this equation, well, this reduction that can be deduced from this equation in ZH, which again, really looks like a bialgebra rule. But anyway, so we are able to prove that all these reduction steps in decision diagrams are provable in ZH, and that gives us essentially what we want. That gives us an algorithm to turn any ZH diagram into a reduced QMDD form. So just before I conclude, I'll give you a little bit of fun stuff that we can see here. So the first one is that I chose this this diagram here in order to gather all the nodes, sorry, all the edges, all the incoming edges in in decision diagrams when we turn them into a ZH diagram. But actually, we could have taken the X spider, or actually any diagram that forms a monoid with ket 0. So it's interesting. And the other interesting thing is, well, we can, when we look at these kinds of equations, we can wonder whether or not this gadget forms some kind of Frobenius algebra. And it's interesting that some equations do hold. Some equations are satisfied, but some other are not. So, for instance, we have some kind of associativity, but we don't have a unit. Also, well, this is not commutative, because if we swap the outputs of this gadget, we get, well, we have to correct for it using a NOT gate on the control wire. And also, it satisfies the Frobenius equation, but again, it's not a proper Frobenius algebra. And it also satisfies the property of being special, if it were a Frobenius algebra. So, to sum up, we have a sound translation from decision diagrams to ZH diagrams. We also have an algorithm that turns any ZH diagram to reduced QMDD form. So actually, it also allows us to extract a decision diagram from any ZH diagram. And as a byproduct, we also get a new completeness proof. Also, this reduction of decision diagrams, when expressed as ZH derivations, shows some interesting structure on the gadgets we use for the translations. And so, if we want to go any further, well, I think one interesting point now is to try and exploit this connection between the two formalisms. So maybe you can use some tools that were developed in decision diagrams for ZH or vice versa. I wonder also if it's possible to exploit redundancy in similar fashion, but for other normal forms, because, well, there exist several kinds of normal forms now for ZH and ZX diagrams. And also, it could be interesting maybe to have a more in-depth and formal look at this weird structure that these gadgets exhibit. So that's it for me, and thanks for your attention.
Let's thank Renaud. Are there any questions?
Yes, so I've got a question. I was wondering whether the way that you use redundancy in these reduced QMDD forms, does that allow you to distinguish between entangled and non-entangled states? Because that's kind of, yeah, one of the things that's a little bit awkward about the standard normal forms, that we can't actually see whether something is entangled or not, because it's just this big, massively connected diagram.
Yes. it's true. And actually, if you have all your qubits well ordered, like if you have, let's say if you have a quantum state that is separable and it's the tensor product of two smaller quantum states, then indeed we can see the separation, because when we do the tensor product, it's actually a very easy operation to do in decision diagrams, because it will simply, let's say, link the terminal node of the first decision diagram to the root of the second decision diagram. And if we go the other way, that means that whenever we have a bottleneck in the decision diagram, that is the decision diagram reduces to a single node at some depth for some layer. That means that the top of the decision diagram constitutes a completely separable state from the one at the bottom. So in this sense, yes, we can see that parts of the diagram are not entangled.
Okay, yeah, that's really cool. Yeah, I see, it makes sense that it would depend on the order in which the qubits are listed. Yeah. But yeah, that seems really useful.
Yeah, I didn't emphasize on this part, but it's I think it's a pretty powerful property for decision diagrams to be able to perform tensor products in a way that's in constant time. Actually, we just have to remove some stuff and add a link, and that's it.
And yeah, maybe a related second question. So one of the generators that you used is exactly, as you explained, sort of something that really comes from ZW. Yes. Why did you use ZH here, not ZW, say?
It's just a matter of convenience, I think. I didn't use ZX because, I could have. I would have needed the algebraic ZX, because we want to have the weights,
right? Yeah.
On a single, like something like that, which we can do in non-algebraic ZX. But ZW allows us to do that. The reason I didn't choose ZW, I don't know. Maybe I'm just more familiar with ZH.
Yeah. I'm just thinking, yeah, there might be something interesting to look at.
I guess it's simply that the two gadgets here are easily representable in ZH, and I didn't check whether or not they were simply enough in ZW. Maybe they are simpler. I don't know.
Okay. Yeah. Thanks. That was really interesting.
I have kind of like a comment, kind of like on these like structures that kind of look like Frobenius algebras or whatever, or not just this, but these various things that you mentioned. Like it seems to me like they still look like they're like distributive laws, or like maybe some generalization of it, but like not exactly. Like one of them is like a Kleisli, like one-sided distributive law kind of thing.
I'm not very familiar with this, but I think there might be something like this going on, because we deal with this control wire by using the fact that we have a monoid on this control space, let's say, which is given simply by the Z spiders. So that's why I used here this unit as the default one, because I think that's what we should get. Because if we compose it with another diagram that also has a control wire, naturally we're going to gather the two controls wires using this Z spider, and if we have so that makes sense. We use this unit here, because we're using this Z spider. But anyway, yeah, I think there's probably something to do with Clay-Slee categories, maybe something like that. But anyway, I didn't look very much into the details.
So it looks pretty interesting.
Yeah. Also, I think part, if not a lot of what we get here when we make this gadget interact with the others really comes from the fact that here, hidden inside this gadget, we have a control swap, which really interacts nicely with a lot of other generators. So I'm not sure, because I don't have my notes under my nose, but I think this would work for any gadget here that constitutes a monoid with cat 0, because this cat 0 it appears in the description of this gadget here. And so a lot of distributive laws we get, we can simply understand them because this here is a control swap, and what we get from the wire that's not the identity, we get the cat 0, which is simply the unit for this monoid. I don't know if I make a lot of sense, but
thanks. Are there any more questions?
Yeah, I'd like to ask about. So I have this idea that ZH normal form.
Mm-hmm.
So this is smaller, or like not exponential, if you have many ones in your matrix or many repeated elements in your matrix, because then you can combine H boxes.
Yeah.
And this QMDD is small when you have many repeated parts.
Yes, and many zeros as well.
And many zeros, yeah.
Yeah.
So is there any hope that we can combine these two features and have something which is like efficient both when you have many zeros and when you have many ones, or like repeated structure, but also just repeated elements throughout the thing? That's
an interesting question. It's definitely something I would like to have a look at. Right now, I don't really have an answer for that. I don't even know if we could do something similar for the ZH normal form, where we could have something that is efficient not only when we have a lot of ones, but also when we have redundancy. That would already be interesting. Yeah. And then merging the two approaches would be could be interesting indeed, but quite hard as well.
There's also this thing about if you change the ordering of your qubits, then sometimes you can get more redundancy, right? That's also an important bit. But
yes, it's something you can find also in decision diagrams, plain decision diagrams, where we know some problems for which, if we have the right ordering of variables, then we have a decision diagram that is linear in size. And if we take the wrong one, then we get something that's exponential in size. So it's very important to have this good ordering. And actually, for the quantum decision diagram part, there exists a procedure called sifting, I think, which is essentially the same as for classical decision diagrams, which tries to look for a good, not the best, but a good ordering. And simply what it does, it looks for, it takes one variable at a time, moves it around the other, changes its ordering with respect to the others, keeps the best, and then you do it for every variable. So you have an algorithm that's quadratic in the number of variables.
Okay.
But obviously it doesn't give you always the best. It gives you a local minimum if you want, and not the global minimum. But indeed, this is important for the size of the diagram.
Cool.
I have like a meta question, kind of. So like, obviously this kind of translation, or this use of the quantum multivalued decision diagrams could be useful to the ZX people. Is there like some quantum multivalued decision diagram like group of people that are like really into this, or is this just some like tool that people use, and could they benefit from like ZH or ZX?
I don't know if, well, this seems to be a very different community. I don't know if they have, this community has heard about ZH. Maybe they have, because we can see sometimes talks at QPL or things like that for that use decision diagrams. But I don't know if so far if we can get something from ZH to the decision diagrams. It's a good question. Well, something that might be interesting to them, to this other community, is the fact that I think so far they have focused a lot on unitary operators, obviously, but their diagrams allow us to represent more. They can represent any morphism of the category qubit, actually. And so that ZH at least gives a nice, let's say, nice codomain for translation from decision diagrams, for completely arbitrary decision diagrams, to something else.
So I think in this talk you only talked about states, essentially, so only things that have outputs. If you have inputs and outputs, is there some way in which we can view this thing as flowing from inputs to outputs, or is that not really? Because you can sort of go down this hierarchy of things, but that's not really going down from inputs to outputs, because it's all outputs.
Indeed, yeah. I guess if you really wanted to have, you know, your inputs at the top and your outputs at the bottom, you would have this decision diagram, but this time going right to the right or to the left, and then you would simply move, but this time from right to left. Yeah, I think I see what you would like to do. I guess something that has the root at the center, and then a decision diagram going up and a decision diagram going down.
Yeah, maybe something.
But yeah, you would need links between the two, because if you only had this root that links the two sub diagrams, that would mean that the inputs and the outputs are separable. So you
so I would imagine that if you have a very compressed decision diagram, that you would have sort of like a funnel, kind of like from inputs, and you funnel stuff to very small sub diagram, and then you funnel it out again. Maybe something like that. I don't know if that's
maybe. I'm not entirely sure you can do that, but yeah, it can be interesting.
Any more questions? In that case, let's thank Renaud again.
Thanks for your attention.
Okay. Nice talk. I don't know anything about quantum multivalued decision diagrams before this.
Me neither.
Yeah, I think I saw.
This was a really clear explanation, Renaud. That was very good. Thanks.
Okay. It's always hard to tell with this.